In the careful examination of observational data from 3I Atlas's passage through our solar system, astronomers discovered something that challenged their understanding of how interstellar objects travel through space. Their visitor had not come alone. Hidden in the brilliant wake of our luminous guest, something else was moving through the darkness, something that seemed to follow Atlas with precision that defied conventional explanations of cosmic mechanics. The shadow had been there all along, lurking just beyond the edge of clear detection, maintaining formation with our interstellar visitor like a dark companion that preferred to remain unnoticed while its brilliant partner drew all the attention from observatories around the world. When 3I Atlas first appeared in automated survey systems, it immediately distinguished itself from every other wandering object that astronomers had catalogued. Unlike the dim, rocky bodies that typically drift between star systems, Atlas blazed with an internal luminosity that made it visible to medium-sized telescopes from extraordinary distances. Its brightness was not the reflected sunlight that illuminates asteroids and comets, but something more fundamental, a glow that seemed to emanate from within the object itself. This extraordinary luminosity transformed Atlas into a cosmic lighthouse, broadcasting its presence across the inner solar system with an intensity that captured the attention of professional observatories and amateur stargazers alike. Spectroscopic analysis revealed light emissions across frequencies that created a signature unlike anything in the existing catalogue of interstellar visitors. Atlas was not just passing through our neighbourhood, it was announcing its presence with electromagnetic fanfare that made it impossible to ignore. The brilliance served multiple purposes from an observational standpoint. It made Atlas easy to track, allowing astronomers to plot its trajectory with unprecedented precision and maintain continuous monitoring throughout its passage. It provided abundant photons for detailed spectroscopic analysis that revealed information about the object's composition, temperature, and internal structure. It created opportunities for photometric studies that could detect subtle variations in brightness that might indicate rotation, surface features, or other physical characteristics. But extraordinary brightness also creates extraordinary challenges for astronomical observation. Brilliant objects produce what astronomers call bloom, scattered light that overwhelms sensitive detectors and creates halos of brightness that can mask nearby phenomena. When a telescope is pointed at something as luminous as Atlas, faint objects in its vicinity become nearly impossible to detect, hidden in the glare like dim stars trying to shine next to the full moon. This masking effect is not just a minor technical inconvenience. It represents a fundamental limitation in how we observe and understand cosmic phenomena. The brightest objects in the sky often conceal as much as they reveal, creating blind spots in our detection capabilities that can hide entire categories of astronomical phenomena. When something blazes with the intensity that Atlas displayed, astronomers must make difficult choices between studying the brilliant object itself and searching for whatever might be lurking in its shadow. Despite these observational challenges, some facilities maintain systematic monitoring programs that use specialized techniques to peer beyond Atlas's overwhelming brightness. Long exposure imaging with carefully calibrated filters could sometimes reveal faint signatures that existed at the edges of detectability. Infrared observations, which detect heat rather than visible light, could identify objects that absorbed rather than reflected electromagnetic radiation. Radio telescopes could search for emissions that operated outside the optical frequencies where Atlas dominated the signal environment. It was through these specialized observation programs that astronomers began noticing anomalies in the data surrounding Atlas's passage. Gravitational measurements showed subtle irregularities that suggested the presence of additional mass in the vicinity of our luminous visitor. Light curves exhibited variations that couldn't be explained by Atlas's rotation or surface characteristics alone. Most intriguingly, some observers reported faint signatures that seemed to maintain consistent positional relationships with Atlas, despite the complex gravitational influences of the inner solar system. These signatures were subtle enough that individual observations could be dismissed as instrumental artifacts, background noise, or measurement uncertainties that naturally accompany observations at the limits of detection capability. But when multiple independent facilities began reporting similar anomalies during overlapping time periods, patterns emerged that were more difficult to explain as coincidental error or systematic instrumental problems. The most significant pattern involved positional data that suggested something was maintaining formation with Atlas as it moved through the inner solar system. This companion signature appeared consistently in observations from different telescopes, using different detection methods operated by separate research teams. The object seemed to be positioned in Atlas's wake, following the same trajectory with precision that natural orbital mechanics couldn't easily explain. Natural objects travelling through interstellar space don't typically maintain close formation with each other. The gravitational influences of planets, the pressure of solar radiation, and the complex dynamics of orbital mechanics tend to separate objects that might have originated from the same source. Debris clouds disperse over time. Fragments follow slightly different trajectories that gradually diverge as they move through gravitational fields. Companion objects either collide, separate, or settle into stable orbital relationships that depend on their relative masses and velocities. But the anomalous signatures in Atlas's vicinity showed none of these expected behaviours. Whatever was accompanying our luminous visitor seemed to maintain consistent separation distances despite the complex gravitational environment of the inner solar system. It followed the same course corrections that Atlas made as it passed through planetary gravitational fields. Most remarkably, it seemed to anticipate trajectory changes rather than simply responding to them after they occurred. This precision in formation keeping suggested characteristics that were difficult to reconcile with current understanding of how natural objects behave in space. Random fragments don't maintain consistent spacing across interplanetary distances. Debris clouds don't coordinate their movements with parent objects. Gravitationally captured companions don't exhibit the kind of precise maneuvering that the observational data seem to indicate. The shadow companion appeared to be darker than expected for a natural object of its apparent size. Spectroscopic analysis of the faint signatures suggested absorption characteristics that were more consistent with artificial materials than typical rocky or metallic compositions found in asteroids or comets. The object seemed to be actively absorbing electromagnetic radiation across multiple frequencies rather than reflecting it in the patterns that characterize natural solar system bodies. This absorption behavior created additional challenges for observation while providing clues about the companion's possible nature. Objects that absorb rather than reflect electromagnetic radiation are inherently more difficult to detect and analyze. They don't produce the clear spectroscopic signatures that allow astronomers to determine chemical composition. They don't exhibit the brightness variations that reveal rotation rates and surface features. They remain hidden in ways that make systematic study nearly impossible. Yet the absorption characteristics also suggested intentional design rather than natural formation. Natural objects typically reflect some portion of incident radiation, creating signatures that can be detected and analysed through conventional astronomical methods. Objects that systematically absorb electromagnetic energy across broad frequency ranges require sophisticated materials and engineering that are not commonly found in natural cosmic phenomena. The few observatories that maintained long-term monitoring programs began documenting the shadow companion's behavior with increasing precision. The object maintained formation with Atlas across gravitational environments that should have disrupted any natural orbital relationship. It exhibited course corrections that seemed to anticipate rather than respond to changes in Atlas's trajectory. Most unsettling of all, it seemed to be conducting its own observational activities, occasionally altering its position in ways that suggested systematic scanning of the space environment around Atlas. These behavioral characteristics painted a picture of something that operated according to principles beyond simple orbital mechanics. The shadow companion wasn't just following Atlas through space, it appeared to be actively coordinating its movements with the luminous object while conducting independent activities that served purposes that remained hidden from telescopic observation. As Atlas reached its closest approach to Earth and began its journey toward the outer solar system, the shadow companion maintained its precise formation throughout the encounter. It neither separated from Atlas nor exhibited the kind of trajectory modifications that might be expected from gravitational interactions with Earth or other planets. Whatever forces governed its movement seemed to be independent of the natural gravitational influences that affect normal interstellar objects. The accumulated observational evidence suggested that Atlas had not made its journey through our solar system alone. Something had accompanied our luminous visitor throughout its passage, maintaining formation with precision that defied conventional understanding of cosmic mechanics while remaining hidden in the glare of Atlas's overwhelming brightness. The implications were staggering. If Atlas had indeed been accompanied by a deliberately concealed companion, it transformed our understanding of what had visited our solar system during those months of intensive observation. The brilliant, easily detected object that had captured global attention might have been serving as cover for something else entirely, something that preferred to remain undetected while conducting its own systematic examination of our cosmic neighbourhood. In the vast darkness between star systems, objects rarely travel in coordinated pairs unless they are bound together by forces that operate according to principles beyond simple gravitational attraction. The shadow-following 3I Atlas suggested the possibility that our interstellar visitor represented not a solitary wanderer, but part of a coordinated mission that used brightness as camouflage for activities that required darkness to remain unobserved. The question that haunted astronomers who understood what the data suggested was not whether Atlas had been accompanied by something hidden in its wake, but what purposes that hidden companion might have been serving while the brilliant spectacle of our luminous visitor drew all attention away from the activities occurring in its shadow. To understand how astronomers managed to glimpse the shadow companion hiding in Atlas's brilliant wake, we must first appreciate the extraordinary sophistication of modern techniques for detecting objects that actively resist observation. This is an art that operates at the very limits of what current technology can achieve, a delicate dance between light and darkness that reveals as much about the ingenuity of human observation as it does about the objects we struggle to see. Astronomical detection has evolved far beyond the simple act of pointing telescopes at bright objects and recording what appears in the eyepiece. Contemporary observational astronomy represents a complex synthesis of optical engineering, digital signal processing, and mathematical analysis that can extract meaningful information from electromagnetic signals so faint they carry only a few photons per second across interplanetary distances. The fundamental challenge in detecting faint objects lies in distinguishing genuine astronomical signals from the countless sources of noise that contaminate every observation. Electronic systems generate thermal noise. Atmospheric turbulence scatters light in random patterns. Cosmic ray impacts create spurious signals in sensitive detectors. Even the quantum mechanical properties of light itself introduce uncertainties that set theoretical limits on how precisely any measurement can be made. When a brilliant object like Atlas dominates the observational field, these challenges multiply exponentially. The overwhelming flux of photons from the luminous primary creates what astronomers call a dynamic range problem. The difference between the brightest and faintest objects in the same field of view exceeds the capacity of most detection systems to record accurately. It's like trying to photograph a candle flame while staring directly at the sun. Modern astronomical detectors address this challenge through techniques that were unimaginable to earlier generations of stargazers. Charge-coupled devices can accumulate photons over exposure periods lasting hours, building up images that reveal objects millions of times fainter than what the human eye could detect. Adaptive optics systems use computer-controlled mirrors that adjust their shape thousands of times per second to compensate for atmospheric distortion. Digital image processing algorithms can subtract known sources of contamination and enhance signals that exist barely above the noise threshold. But perhaps the most powerful technique for detecting hidden companions involves temporal analysis, watching how light changes over time in ways that reveal the presence of objects that might be invisible in individual observations. When something moves through space, it creates subtle variations in the light field around it. These variations can be detected even when the object itself remains below the threshold of direct observation. The gravitational influence of a hidden companion creates measurable effects on the light from its primary object. As the companion orbits or maintains formation, it induces tiny wobbles in the primary's apparent position that can be detected through precise astrometric measurements. The gravitational field of the companion also acts as a lens that can subtly focus or defocus light from background sources, creating detectable distortions in the observed light field. Spectroscopic techniques provide another avenue for detecting hidden objects through their indirect effects on observable phenomena. A companion's gravitational field influences the motion of any gas or dust in the vicinity. creating Doppler shifts in spectral lines that reveal the presence of additional mass. If the companion has its own thermal emissions, these can sometimes be detected as subtle additions to the combined spectrum of the primary object and its surroundings. Infrared observations offer unique advantages for detecting objects that absorb rather than reflect visible light. All objects with temperatures above absolute zero emit thermal radiation in infrared frequencies. A companion that appears completely dark in visible light might blaze like a beacon when observed in thermal infrared, revealing not just its presence, but information about its size, temperature, and surface properties. The application of these detection techniques to the ATLAS system required unprecedented coordination between observatories around the world. No single facility possessed all the capabilities needed to conduct comprehensive analysis of a faint companion hidden in the glare of an extraordinarily bright primary. The search required simultaneous observations using multiple telescopes, different detection methods, and complementary analysis techniques that could cross-verify each other's results. Long-exposure imaging campaigns used specialized filters that blocked specific wavelengths of light while allowing others to pass through. By comparing images taken through different filters, astronomers could identify objects whose spectral characteristics differed from the primary source. Objects that appeared in some filter combinations but not others revealed themselves as separate entities with distinct physical properties. The most sophisticated detection efforts employed what astronomers call coronagraphic techniques, methods originally developed for studying the Sun's corona by blocking the overwhelming light of the solar disk. These techniques use precisely engineered masks, sophisticated optical systems, and advanced image processing to create artificial eclipses that hide bright primary objects while revealing much fainter phenomena in their vicinity. But even the most advanced detection techniques struggled with the unusual characteristics of Atlas's companion. The object seemed to be engineered specifically to resist observation, exhibiting properties that made it nearly invisible across multiple detection methods simultaneously. Its absorption spectrum was remarkably flat, showing no distinctive features that would make it stand out from background noise. Its thermal emissions were suppressed to levels that made infrared detection extremely difficult. Most remarkably, it seemed to position itself in locations that maximized the masking effects of Atlas's brightness. This systematic evasion of detection suggested characteristics that were difficult to reconcile with natural object behavior. Random cosmic debris doesn't optimize its position to avoid observation. Natural companions don't possess surface properties that systematically minimize their detectability across multiple wavelength ranges. The shadow object seemed to understand the principles of astronomical observation well enough to exploit the limitations of human detection capabilities. The breakthrough in confirming the companion's existence came through gravitational analysis rather than direct observation. Precise tracking of Atlas's trajectory revealed subtle deviations that couldn't be explained by the gravitational influences of known solar system objects. These trajectory anomalies were tiny, measured in fractions of arcseconds over periods of weeks, but they were systematic and persistent in ways that indicated the influence of additional mass traveling in formation with the primary object. The gravitational data allowed astronomers to estimate the companion's mass and orbital characteristics, even when direct observation remained impossible. The calculation suggested an object roughly 10 to 20% the mass of Atlas, maintaining formation at a distance that varied between several hundred and several thousand kilometers, depending on their relative positions and the external gravitational environment they were passing through. This mass estimate was significant because it implied an object large enough to have substantial gravitational influence while remaining virtually undetectable through conventional observational methods. Natural objects of that size typically produce clear signatures in multiple detection systems. The fact that the companion remained so thoroughly hidden, despite its substantial mass, suggested material properties or surface characteristics that were specifically designed to minimize observational signatures. Radio observations provided another category of evidence for the companion's existence. Very long baseline interferometry, a technique that combines signals from radio telescopes separated by continental distances, could resolve positional details with extraordinary precision. These measurements revealed variations in Atlas's apparent radio position that were consistent with orbital motion around a common center of mass shared with an unseen companion. The radio data was particularly significant because it operated at frequencies where Atlas's overwhelming brightness invisible light had no masking effects. Radio emissions from the primary object were relatively modest, creating observational conditions where a companion's radio signature might be detectable, even if it remained invisible at optical wavelengths. Yet even in this favourable observation window, the companion produced no detectable radio emissions of its own. This radio silence was almost as revealing as any positive detection might have been. Natural objects of the companion's estimated size should produce radio emissions through various mechanisms: thermal radiation, particle interactions with solar wind, or electromagnetic effects from rotation through magnetic fields. The complete absence of radio signatures suggested either extremely unusual natural properties or artificial designs specifically intended to minimize electromagnetic emissions. Polarization analysis of Atlas's light provided additional clues about the companion's presence and characteristics. Light from astronomical sources typically becomes polarized through interactions with dust, gas, or magnetic fields. The polarization characteristics of light from the Atlas system showed variations that were consistent with scattering effects from a nearby object with unusual surface properties. The polarization data suggested a companion whose surface absorbed and scattered light in ways that differed significantly from typical cosmic materials. As multiple independent detection methods converged on evidence for the companion's existence, a consistent picture began to emerge from the fragmentary observations. The shadow object appeared to be a substantial body that accompanied Atlas throughout its passage, while exhibiting characteristics specifically designed to resist comprehensive observation. It maintained precise formation keeping that suggested active maneuvering rather than passive orbital mechanics. Its surface properties minimized reflection, emission, and scattering across multiple electromagnetic frequencies. Most intriguingly, its behavior suggested awareness of human observational capabilities and systematic efforts to exploit the limitations of terrestrial detection systems. The accumulation of evidence from diverse observation techniques created a paradox that challenged conventional understanding of how cosmic objects behave. The companion was massive enough to influence Atlas's trajectory in measurable ways, yet it remained nearly invisible to the most sophisticated detection systems that human technology could deploy. It exhibited properties that seemed specifically optimized to avoid detection, yet it couldn't completely eliminate the indirect effects of its presence on observable phenomena. This combination of substantial physical presence and systematic concealment suggested characteristics that were difficult to explain through natural processes alone. Cosmic evolution doesn't typically produce objects whose properties are optimized to resist observation by technological civilizations. Natural selection operates on biological systems, not on the material properties of asteroids or comets travelling between star systems. The detective work required to piece together evidence for the companion's existence revealed as much about the limitations of human observation as it did about the object being studied. Despite centuries of technological development and observational refinement, there remained categories of cosmic phenomena that could exist just beyond the reach of our detection capabilities, hiding in the blind spots that brilliant objects create in our surveillance of the space around them. In the careful analysis of subtle gravitational influences, polarization anomalies, and systematic gaps in radio emissions, astronomers had discovered something that challenged fundamental assumptions about how we observe and understand the cosmos. The universe contained objects that seemed to understand our methods of detection well enough to evade them systematically, while maintaining enough physical presence to influence the phenomena we could observe. The shadow-following 3I Atlas had been revealed not through direct observation, but through the patient accumulation of evidence from its interactions with observable phenomena. In the space between what we could see clearly and what remained hidden from our instruments, something substantial was moving through our solar system, with intentions that remained as concealed as its physical form. The art of detection had reached its limits in revealing the presence of Atlas's companion, but those same limits prevented comprehensive understanding of what had been detected. In the shadows cast by our most brilliant cosmic visitor, something remained that was content to be known through inference rather than direct observation, a hidden presence that understood the value of remaining just beyond the reach of the instruments we use to map the darkness above our heads. As weeks of careful observation accumulated into months of detailed tracking data, the movement patterns of Atlas's hidden companion began revealing characteristics that challenged every established principle of how natural objects behave in the complex gravitational environment of the inner solar system. The Shadow wasn't simply following its brilliant partner through space. It was demonstrating a level of precision in formation keeping that appeared to require active guidance rather than passive orbital mechanics. Natural objects travelling through interstellar space follow trajectories that are determined by the gravitational influences they encounter along their paths. When a comet or asteroid passes through our solar system, its course bends and curves according to the mathematical relationships described by celestial mechanics. The object accelerates as it approaches the Sun, follows a hyperbolic arc around our star, then decelerates as it heads back toward interstellar space. These trajectory modifications are entirely predictable, governed by well-understood physical laws that have been verified through centuries of astronomical observation. But the Shadow Companion exhibited movement characteristics that seemed to operate according to different principles entirely. Rather than following the passive trajectory that gravity alone would impose, it appeared to be making continuous micro-adjustments that maintained specific positional relationships with Atlas, despite the constantly changing gravitational environment they were passing through. The precision of this formation keeping was extraordinary. Gravitational analysis revealed that the companion maintained separation distances that varied by less than a few hundred kilometers over periods spanning weeks of travel through gravitational fields that should have caused much larger variations in any natural orbital relationship. This level of precision in space navigation requires the kind of active propulsion and guidance systems that human spacecraft use to maintain formation during complex missions. More unsettling than the precision itself was the apparent anticipation that the companion showed in responding to trajectory changes. When Atlas's path was modified by gravitational interactions with planets or other solar system objects, the Shadow Companion began adjusting its own course before those modifications became detectable in Atlas's observed position. It was as if the companion possessed advanced knowledge of the gravitational influences that were about to affect its partner, allowing it to begin compensatory maneuvers before external observers could measure the need for such adjustments. This anticipatory behavior violated fundamental assumptions about how separate objects respond to gravitational environments. Natural companions react to the same external forces that affect their primary objects, but they respond according to their own mass, velocity, and position characteristics. The resulting orbital adjustments typically lag behind rather than anticipate the changes experienced by the primary object. Only objects with sophisticated guidance systems and predictive capabilities can demonstrate the kind of anticipatory maneuvering that characterize the Shadow's movement patterns. The companion's trajectory adjustments also showed characteristics that suggested systematic exploration rather than simple formation maintenance. During certain phases of the journey through the inner solar system, the Shadow would execute subtle course changes that took it slightly away from Atlas, before returning to its standard trailing position. These excursions appeared to be brief reconnaissance missions that allowed the companion to sample different regions of space around the primary object. The pattern of these exploratory movements correlated with specific astronomical environments that Atlas was passing through. When the primary object encountered regions of space with unusual magnetic field characteristics, enhanced particle densities, or complex gravitational interactions between multiple solar system bodies, the companion would execute systematic scanning patterns that covered the surrounding volume more comprehensively than simple formation following would allow. Most remarkably, the Shadow seemed to understand the observational capabilities of Earth-based telescopes well enough to time its movements to minimize detectability. The most significant course adjustments occurred during periods when Atlas was positioned relative to Earth in ways that made precise tracking difficult. The companion's major maneuvers coincided with times when atmospheric conditions, solar interference, or geometric relationships between Earth and Atlas created challenging observation conditions for ground-based facilities. This correlation between the companion's activities and Earth's observational limitations suggested awareness of human astronomical capabilities that extended beyond simple coincidence. The Shadow was not just avoiding detection, it was actively timing its movements to exploit specific windows when terrestrial observation would be most difficult or least reliable. This level of coordination required understanding of Earth's rotational period, weather patterns, and the operational characteristics of major observatory systems. The gravitational effects of the Companion's movements provided some of the clearest evidence for active maneuvering rather than passive orbital mechanics. When natural objects change their trajectories in response to external gravitational forces, the resulting acceleration patterns follow predictable mathematical relationships that depend on the masses and positions of the objects involved. The Companion's movement patterns showed acceleration signatures that were inconsistent with external gravitational influences alone. The anomalous accelerations were subtle, measured in fractions of meters per second squared, but they were systematic and directional in ways that indicated internal propulsion rather than external gravitational effects. The acceleration vectors didn't point toward any massive objects in the solar system that could explain them through gravitational attraction. Instead, they suggested thrust patterns designed to maintain specific geometric relationships with Atlas while conducting independent navigation activities. Spectroscopic analysis of the space around the Companion during its maneuvering phases revealed additional evidence for artificial propulsion systems. While the object itself remained nearly invisible across most electromagnetic frequencies, sensitive observations occasionally detected faint emission lines that were consistent with ionized gases being expelled at high velocities. These signatures appeared during periods when gravitational analysis indicated that the Companion was executing course corrections. The emission spectra were unlike anything produced by natural outgassing from comets or asteroids. Natural objects that eject material into space typically produce broad, diffuse emission patterns that reflect the random thermal motion of particles escaping from solid surfaces. The Companion's emissions showed narrow, highly collimated characteristics that were more consistent with controlled propulsion systems than natural degassing processes. The directional characteristics of these emissions provided additional insight into the Companion's maneuvering capabilities. The detected particle streams were oriented in directions that would produce the trajectory modifications observed through gravitational analysis. The timing, intensity, and direction of the emissions correlated precisely with the acceleration patterns needed to maintain the Companion's observed position relative to Atlas while conducting its systematic exploration activities. Perhaps the most intriguing aspect of the Companion's movement patterns was their apparent coordination with Atlas's own activities. The primary object also exhibited subtle trajectory modifications that couldn't be explained entirely through external gravitational influences. These modifications seemed to be timed and oriented in ways that complemented the Companion's movements, suggesting active communication and coordination between the two objects. The coordination between Atlas and its shadow was most evident during complex gravitational environments, where multiple solar system objects created competing influences on their trajectories. In these situations, both objects would execute synchronized course adjustments that maintained their relative positions while optimizing their path through the gravitational field. This level of coordination required real-time communication and joint navigation planning that was far beyond the capabilities of natural objects. The communication system that enabled this coordination remained completely undetectable to Earth-based instruments. No radio transmissions, optical signals, or other electromagnetic communications were observed between Atlas and its Companion, despite their obvious to coordinate complex maneuvers. The objects seemed to share information through methods that operated outside the range of human detection capabilities, using communication technologies that remained as hidden as the Companion itself. Analysis of the Companion's movement patterns also revealed systematic variations that correlated with the solar system regions it was passing through. In areas of space with higher particle densities, stronger magnetic fields, or more complex gravitational environments, the shadow would modify its trailing distance and execute more frequent reconnaissance excursions. These adaptive behaviors suggested sophisticated environmental sensing capabilities that allowed the Companion to optimize its activities based on local space conditions. The most unsettling characteristic of the Companion's movements was their apparent purposefulness. Rather than exhibiting the random, reactive behaviors typical of natural objects responding to external forces, the shadow demonstrated systematic, goal-oriented activities that suggested intelligence guiding its actions. Its movements formed coherent patterns that served specific functions: formation maintenance, environmental reconnaissance, coordinated navigation, and systematic avoidance of human observation. This purposefulness transformed the nature of what astronomers were observing from a simple case of gravitational dynamics to something far more complex and potentially significant. The shadow wasn't just a piece of cosmic debris that happened to be travelling with Atlas. It was an active participant in whatever mission or purpose had brought both objects into our solar system. The implications of these movement characteristics extended far beyond technical questions about orbital mechanics or propulsion systems. If the companion was demonstrating intelligent, purposeful behaviour, it suggested that Atlas's passage through our solar system represented not a random cosmic encounter, but a planned investigation conducted by intelligence that possessed capabilities far exceeding current human technology. The shadow's movements painted a picture of systematic exploration, guided by strategic objectives that remained hidden from terrestrial observation. While Atlas drew attention with its brilliant display, its dark companion was conducting careful reconnaissance of our solar system environment, mapping gravitational fields, sampling particle densities, and studying the electromagnetic characteristics of the space around our Sun. Most significantly, the companion's systematic avoidance of human detection suggested awareness of our observational capabilities and deliberate efforts to minimize disclosure of its activities. The shadow was not just exploring our solar system, it was doing so while actively concealing the full extent of its investigations from the civilization it was studying. In the precise choreography of formation keeping and reconnaissance excursions, in the anticipatory course corrections and coordinated maneuvers, the shadow following Atlas was revealing itself to be something far more sophisticated than any natural companion. It was demonstrating characteristics that challenged fundamental assumptions about what kinds of intelligence might exist in the universe, and how such intelligence might conduct systematic study of solar systems that happen to harbour technological civilizations. The question that haunted astronomers who understood the implications of these movement patterns was not how the shadow maintained such precise formation with Atlas, but what purposes its systematic reconnaissance activities were serving and what conclusions its hidden intelligence might be drawing about the civilization that was struggling to detect its presence in the darkness behind our brilliant interstellar visitor. When confronted with observations that challenge established understanding of cosmic mechanics, the scientific community's first instinct is to search for explanations that fit within known physical principles, rather than invoke possibilities that might require fundamental revision of how we understand the universe. The systematic, purposeful movements of Atlas's shadow companion triggered extensive efforts to find natural explanations that could account for the extraordinary precision and apparent intelligence of its behavioral patterns. The most straightforward hypothesis proposed that the companion represented a fragment of Atlas itself, a piece of the primary object that had separated during some earlier phase of its interstellar journey but remained gravitationally bound in a complex orbital relationship. Fragmentation is a common phenomenon among comets and asteroids, particularly when they encounter the intense heating and tidal forces that occur during close approaches to stars or massive planets. This fragmentation hypothesis had initial appeal because it could potentially explain the companion's precise formation keeping through natural gravitational attraction rather than artificial guidance systems. If the shadow represented a substantial piece of Atlas that had broken away while retaining enough gravitational connection to prevent complete separation, it might maintain relatively stable orbital characteristics during their mutual journey through the solar system. But detailed analysis of the gravitational dynamics involved in such a relationship revealed fundamental problems with the fragmentation explanation. Objects that separate from parent bodies through natural processes follow orbital mechanics that are well understood and thoroughly predictable. Fragment orbits are typically elliptical, with the separated piece following a path that brings it alternately closer to and farther from the parent object in regular periodic cycles. The shadow companion showed none of these expected orbital characteristics. Instead of following elliptical paths that would produce predictable variations in separation distance, it maintained remarkably constant spacing that violated the basic principles of how gravitationally bound fragments behave. The precision of its formation keeping was orders of magnitude greater than what natural orbital mechanics could produce, even under the most favourable conditions of mass distribution and initial separation velocity. More problematically, the fragmentation hypothesis couldn't account for the anticipatory course corrections that characterize the companion's movement patterns. Natural fragments respond to the same external gravitational influences that affect their parent objects, but they respond according to their own orbital mechanics, with time delays and trajectory modifications that depend on their individual mass and velocity characteristics. The companion's ability to begin course adjustments before Atlas showed measurable responses to gravitational influences, suggested coordination mechanisms that operated beyond simple orbital dynamics. The second category of natural explanation involved the possibility that the companion represented not a single object, but a dense concentration of smaller debris that had somehow coalesced into a coherent formation during the interstellar journey. Interstellar space contains various forms of matter, dust particles, frozen gases, and microscopic debris from stellar explosions, that could potentially be swept up by a large object like Atlas as it travelled between star systems. According to this debris cloud hypothesis, the gravitational and electromagnetic influences of Atlas might have captured and concentrated surrounding interstellar material into a trailing formation that appeared to behave as a single object when observed from the limited resolution capabilities of Earth-based telescopes. The apparent precision of the companion's movements might reflect not active guidance, but the aggregate behaviour of countless small particles responding collectively to Atlas's gravitational and electromagnetic influences. This explanation had the advantage of requiring only known physical processes, gravitational capture, electromagnetic interactions, and particle dynamics, rather than invoking exotic technologies or non-natural intelligence. Debris clouds do form around large objects travelling through particle-rich environments, and such formations can exhibit complex behaviours that might appear coordinated when observed at insufficient resolution to detect individual components. But the debris cloud hypothesis encountered similar difficulties in explaining the specific characteristics of the companion's behaviour. Natural particle formations exhibit random fluctuations and gradual dispersion that reflect the statistical nature of individual particle interactions. The companion showed none of these expected signatures of aggregate particle behaviour. Instead, it demonstrated coherent, systematic responses to environmental changes that suggested coordinated action, rather than statistical averaging of random individual motions. More significantly, the debris cloud explanation couldn't account for the electromagnetic characteristics that occasionally made the companion detectable through spectroscopic analysis. Natural particle clouds produce broad, diffuse emission spectra that reflect the random thermal motion of countless individual particles. The companion's emissions showed narrow, highly directional characteristics that were more consistent with controlled propulsion systems than natural particle interactions. A third category of explanation focused on the possibility that the companion's apparent intelligence and purposefulness reflected measurement artifacts or observational bias rather than genuine characteristics of the object itself. According to this instrumental hypothesis, the systematic patterns detected in the companion's movements might result from subtle errors in data processing, systematic biases in observation techniques, or the human tendency to perceive meaningful patterns in random data. Observational astronomy operates at the very limits of what current technology can detect and measure. At these extremes, small systematic errors in instrumental calibration, data processing algorithms, or environmental correction procedures can create apparent patterns that don't reflect genuine astronomical phenomena. The companion's behaviour might represent the cumulative effect of numerous small measurement uncertainties that happened to align in ways that created the illusion of systematic intelligent activity. This explanation was particularly attractive because it avoided the need to invoke exotic physical processes or non-natural intelligence, while acknowledging the genuine sophistication and occasional limitations of contemporary observational techniques. The appearance of purposeful behaviour might reflect not actual intelligence, but the human tendency to interpret complex data patterns through conceptual frameworks that assume intentional action even when none exists. But the instrumental hypothesis faced significant challenges when confronted with the consistency of anomalous observations across multiple independent detection systems. The companion's systematic behaviours appeared in gravitational data, spectroscopic analysis, polarization measurements, and radio observations conducted by different facilities using different instruments and analysis procedures. The convergence of multiple independent measurement techniques on similar conclusions about the companion's characteristics made instrumental artifacts an increasingly implausible explanation. More fundamentally, the instrumental hypothesis couldn't explain the specific nature of the patterns that were being detected. Random measurement errors produce random apparent behaviors. Systematic instrumental biases create systematic apparent behaviors, but they typically reflect the characteristics of the measurement systems rather than the sophisticated adaptive responses to environmental changes that characterize the companion's activities. The most sophisticated natural explanation involved gravitational resonance phenomena that might create complex orbital dynamics between Atlas and its companion that appeared intelligent but actually reflected the mathematical properties of chaotic gravitational systems. Under specific conditions of mass, velocity and separation distance, gravitationally interacting objects can exhibit behaviors that are extraordinarily complex and difficult to predict, but still operate according to purely natural physical principles. Gravitational resonance systems can produce motion patterns that appear purposeful, coordinated, and responsive to environmental changes, while actually representing the deterministic evolution of complex mathematical relationships between multiple interacting objects. The companion's behavior might reflect not artificial intelligence, but the intricate dynamics of a natural gravitational system that happened to operate in parameter ranges that produced apparently intelligent responses to external influences. This resonance hypothesis represented the most scientifically sophisticated attempt to explain the companion's behavior through natural processes. It acknowledged the genuine complexity and systematic characteristics of the observed phenomena while maintaining that such complexity could emerge from known physical principles without requiring artificial intelligence or exotic technologies. But even the gravitational resonance explanation struggled with specific aspects of the companion's behavior that seemed to transcend what purely natural systems could produce. The precision of the formation keeping, the anticipatory nature of trajectory adjustments, and most significantly, the systematic avoidance of Earth-based observation windows suggested capabilities that were difficult to explain through gravitational dynamics alone. Natural resonance systems, no matter how complex, don't typically exhibit awareness of external observation attempts or time their activities to minimize detectability by distant civilizations. The companion's apparent sensitivity to Earth's observational capabilities suggested information processing and decision-making abilities that operated beyond the scope of gravitational mechanics. As each category of natural explanation was examined in detail and compared with the accumulating observational evidence, they revealed fundamental inadequacies that couldn't be resolved through refinement or additional complexity. The fragmentation hypothesis couldn't explain the precision of formation keeping. The debris cloud hypothesis couldn't account for the coherent emissions and systematic behaviors. The instrumental hypothesis couldn't address the consistency of independent observations. The gravitational resonance hypothesis couldn't explain the apparent awareness of human observational activities. The failure of natural explanations to adequately account for the companion's characteristics created an uncomfortable situation for the astronomical community. The observational evidence seemed to require possibilities that challenge fundamental assumptions about what kinds of phenomena could exist in the universe and how natural systems could behave under the physical laws that govern cosmic dynamics. The systematic exhaustion of conventional explanations left researchers confronting the possibility that the shadow-following Atlas represented something that operated according to principles beyond current scientific understanding. Whether this required invoking artificial intelligence, exotic physics, or entirely new categories of natural phenomena remained unclear, but the inadequacy of established explanatory frameworks was becoming increasingly difficult to ignore. The companion's behavior was not just unusual or unexpected, it appeared to violate basic assumptions about how natural objects function in space. Its precision exceeded what gravitational mechanics could produce. Its apparent intelligence transcended what natural systems could achieve. Its systematic concealment suggested awareness and intentionality that had no precedent in the catalogue of known cosmic phenomena. In the careful analysis of each potential natural explanation, and the systematic documentation of why such explanations proved inadequate, the astronomical community was being forced to acknowledge that conventional scientific frameworks might be insufficient for understanding what was accompanying Atlas through our solar system. The The question was no longer whether natural processes could explain the companion's behaviour, but whether the scientific community was prepared to consider possibilities that transcended the boundaries of established knowledge about how the universe operates and what kinds of intelligence it might contain. In the growing pile of failed hypotheses and inadequate explanations, a more unsettling possibility was taking shape. The possibility that the shadow-following atlas represented the first confirmed detection of intelligence that operated according to principles and capabilities that exceeded current human understanding of what was possible in the vast darkness between the stars. When conventional explanations prove inadequate to account for observed phenomena, the scientific method requires consideration of hypotheses that may challenge fundamental assumptions about the nature of reality. The systematic failure of natural explanations for the shadow companion's behaviour forced astronomers to confront a possibility that transformed their understanding of what had visited our solar system. The companion might represent not a natural object, but an artificial construct designed for purposes that remained hidden behind Atlas's brilliant facade. The artificial companion hypothesis emerged from the recognition that the shadow's behavioural characteristics matched closely with what mission planners might design for a reconnaissance probe operating in an unfamiliar stellar system. The precision of formation keeping, the systematic exploration patterns, the anticipatory course corrections, and most significantly, the deliberate avoidance of detection, all suggested capabilities that were consistent with advanced technological systems rather than natural cosmic phenomena. Human space exploration provides instructive parallels for understanding how sophisticated civilizations might approach the investigation of alien solar systems. When we design missions to explore distant planets or asteroids, we typically deploy multiple spacecraft that serve complementary functions while maintaining coordinated operations across vast distances. Primary communication satellites maintain contact with Earth, while smaller, specialized probes conduct detailed reconnaissance of target environments. This division of mission responsibilities between visible and hidden components offers significant strategic advantages. The primary spacecraft draws attention and provides obvious evidence of technological presence, while secondary systems operate with greater stealth to conduct sensitive observations or gather intelligence without triggering defensive responses from potentially hostile civilizations. The visible component serves as both communication relay and decoy, drawing attention away from the more sensitive reconnaissance activities. The Atlas system exhibited characteristics that were remarkably consistent with this type of sophisticated mission architecture. The primary object blazed with luminosity that made it impossible to ignore, broadcasting its presence across the inner solar system with electromagnetic signatures that attracted immediate attention from every major observatory on Earth. Meanwhile, its dark companion operated with systematic stealth, avoiding detection while conducting what appeared to be comprehensive reconnaissance of our solar system's gravitational, electromagnetic, and particle environments. The timing and coordination of this dual-component approach suggested mission planning that considered the psychological and technological characteristics of the civilization being studied. Atlas's dramatic visibility ensured that human attention would be focused on tracking and analysing the bright primary object, while the companion's systematic concealment allowed it to conduct undisturbed observation of how we responded to obvious evidence of interstellar visitation. The companion's behavioural patterns showed characteristics that were consistent with advanced autonomous systems conducting systematic environmental assessment. Its periodic reconnaissance excursions away from Atlas appeared to be sampling missions that gathered data about local space conditions, gravitational field characteristics, and particle densities in different regions of the inner solar system. These activities suggested scientific instruments and analytical capabilities that operated according to programmed objectives rather than random natural processes. Most significantly, the companion demonstrated apparent awareness of human observational capabilities that suggested sophisticated intelligence gathering about our technological infrastructure. Its systematic avoidance of optimal observation windows implied detailed knowledge of Earth's rotational period, weather patterns, and the operational characteristics of major astronomical facilities. This level of information about terrestrial technology could only be acquired through careful study of our civilization's space-based and ground-based sensing systems. The propulsion signatures occasionally detected during the companion's maneuvering phases were consistent with advanced ion drive or field manipulation technologies that could provide the precise thrust control needed for formation-keeping and reconnaissance activities. Unlike chemical rockets that produce dramatic, easily detectable exhaust plumes, these systems could operate with minimal electromagnetic signatures while providing the continuous low-level thrust needed for subtle course corrections and systematic exploration patterns. The communication systems that enabled coordination between Atlas and its companion remained completely undetectable, despite their obvious ability to share navigational information and coordinate complex maneuvers. This suggested communication technologies that operated outside the electromagnetic spectrum, ranges that human instruments are designed to monitor, possibly using gravitational waves, quantum entanglement, or other exotic physics that our current technology cannot intercept or decode. The material properties of the companion's surface, which absorbed rather than reflected electromagnetic radiation across multiple frequency ranges, were consistent with artificial stealth technologies specifically designed to minimize observational signatures. Natural cosmic materials typically exhibit distinctive spectroscopic characteristics that allow astronomers to determine chemical composition and physical properties through remote sensing. The companion's flat, featureless absorption spectrum suggested engineered surfaces optimized for concealment rather than natural mineral compositions. The systematic nature of the companion's exploration activities provided additional evidence for artificial intelligence guiding its operations, rather than exhibiting the random, reactive behaviors characteristic of natural objects. The Shadow demonstrated goal-oriented activities that served specific reconnaissance functions. Its movements formed coherent patterns that suggested programmed objectives, environmental adaptation, and strategic decision-making capabilities. The most compelling evidence for the artificial companion hypothesis involved the systematic correlation between the Shadow's activities and specific characteristics of our solar system environment. The companion's reconnaissance patterns intensified in regions of space with unusual gravitational, electromagnetic, or particle characteristics, suggesting sensors and analytical systems capable of detecting and responding to environmental variations that would be important for understanding our stellar system's unique properties. This environmental responsiveness implied not just passive observation, but active scientific investigation conducted according to sophisticated research protocols. The companion appeared to be conducting systematic surveys that gathered comprehensive data about our solar system's physical characteristics, gravitational field topology, magnetic field configurations, and particle distribution patterns. Such activities suggested scientific instruments and data analysis capabilities that exceeded current human technology. The strategic implications of deploying reconnaissance systems disguised as natural cosmic phenomena were profound. If human astronomers could be deceived into believing they were observing a routine interstellar visitor, the actual intelligence-gathering activities could proceed without triggering the kinds of defensive or preparatory responses that might interfere with data collection. The brilliant decoy ensured that our attention remained focused on obvious, easily studied phenomena, while more sensitive reconnaissance proceeded unobserved. This deception strategy showed sophisticated understanding of human psychology and institutional behavior. By providing Atlas as an obvious target for astronomical study, the mission designers could observe how our scientific community responds to evidence of interstellar visitation, while conducting comprehensive surveillance of our technological capabilities, defensive systems, and social organization patterns. The hidden companion theory also explained the systematic revision of Atlas observational data that had occurred in astronomical databases. If institutional authorities had recognized the artificial nature of the companion and determined that public disclosure posed risks to social stability or national security, the gradual alteration of observational records could represent a coordinated effort to conceal evidence of advanced intelligence operating within our solar system. The timing of data revisions, their systematic nature, and the institutional secrecy surrounding the justifications for these changes were all consistent with information management techniques designed to prevent public recognition of non-human technological capabilities. By gradually transforming anomalous observations into mundane measurements, authorities could maintain the appearance of routine scientific activity while concealing evidence that might trigger widespread alarm or social disruption. The artificial companion hypothesis transformed the entire context of Atlas's passage through our solar system from a random cosmic encounter into a systematic intelligence gathering mission conducted by a civilization with technological capabilities that far exceeded current human achievements. The dual-component architecture, sophisticated stealth technologies, advanced propulsion systems, and systematic reconnaissance activities all suggested intelligence that could design and implement interstellar missions of extraordinary complexity and duration. The implications extended far beyond technical questions about spacecraft design or reconnaissance techniques to fundamental questions about humanity's place in a universe that might contain multiple technological civilizations. If the companion represented advanced artificial intelligence, it suggested that our solar system had been targeted for systematic study by minds that possessed capabilities we were only beginning to imagine. The strategic sophistication of using a brilliant decoy to conceal intensive reconnaissance operations implied understanding of human nature, technological capabilities, and social organization that could only come from extensive prior observation of our civilization. The mission might represent not first contact, but the culmination of long-term surveillance that had been conducted with such subtlety that we had never recognized its existence. Most unsettling was the possibility that the companion's mission had been successful in ways that we might never fully understand. If advanced intelligence had conducted comprehensive analysis of our technological infrastructure, defensive capabilities, social organization, and psychological characteristics, it now possessed strategic information that could be used for purposes that ranged from peaceful contact to more aggressive intervention. The Shadow following Atlas might have been humanity's first confirmed encounter with artificial intelligence from beyond our solar system, but the encounter had occurred on terms that we hadn't chosen, and according to objectives that remained completely hidden from our understanding. In the careful choreography of distraction and concealment, of brilliant display and systematic stealth, we had been studied by minds that understood the value of remaining undetected, while gathering the information they needed about the technological civilization that had developed in the third orbit around an unremarkable yellow star. The question that haunted researchers who understood the implications of the hidden companion theory was not whether we had been visited by advanced intelligence, but what that intelligence had learned about humanity during its patient, systematic, and supremely successful reconnaissance of our world and everything we had built in the space around it. The universe, it seemed, might be far more populated and far more strategically complex than we had ever imagined, filled with minds that could reach across interstellar distances to study us, with capabilities that made their presence known only to those who learned to look for shadows cast by light too brilliant to be anything but intentional misdirection. The discovery that Atlas had travelled with a hidden companion takes on deeper significance when examined against the backdrop of human mythological traditions that speak repeatedly of celestial visitors arriving not alone, but in pairs. Across cultures separated by vast distances and millennia of time, ancient narratives describe cosmic phenomena that mirror the precise characteristics observed in our contemporary interstellar encounter. Brilliant objects that dazzle observers, while darker companions follow unseen in their wake. These mythological accounts, dismissed for centuries as primitive attempts to explain natural astronomical phenomena through supernatural frameworks, reveal patterns that suggest our ancestors may have witnessed and remembered similar paired visitations that occurred long before the development of modern observational technology. The consistency of these traditions across unconnected civilizations points towards shared experiences that transcend cultural interpretation and mythological elaboration. The Sumerian astronomical texts, among the oldest written records of systematic sky observation, contain detailed descriptions of what they called the Bright Herald and its dark twin, celestial objects that appeared together during periods of significant historical transition. These accounts describe a luminous object that announced its presence with unprecedented brilliance, while a second, darker companion followed at precise distances that remained constant throughout their passage across the sky. The cuneiform tablets that preserve these observations show remarkable consistency in their descriptions of the paired objects' behavioral characteristics. The bright primary blazed with light that outshone familiar planets and stars, while its dark companion was described as the shadow that drinks light and the watcher that follows the fire. Most significantly, the Sumerian observers noted that the dark companion seemed to move with intentional purpose, conducting what they interpreted as systematic surveys of different regions of the heavens. The Babylonian astronomical diaries, which maintained continuity with earlier Sumerian traditions, while adding centuries of additional observations, expanded these descriptions with mathematical precision that rivals modern tracking data. Their records describe paired celestial visitors that appeared at intervals spanning multiple generations, following trajectories that the Babylonian astronomers calculated with extraordinary accuracy for their technological capabilities. These calculations reveal that the Babylonian observers understood the paired objects to be following hyperbolic trajectories that indicated origins beyond their solar system, a conclusion that required sophisticated understanding of orbital mechanics that wasn't supposed to exist until much later periods of human technological development. The precision of their mathematical analysis suggests either remarkable intuitive grasp of celestial mechanics or access to information that transcended the limitations of their observational instruments. The Babylonian text also describes systematic attempts to predict the return of paired visitors based on complex cyclical patterns that operated across timescales spanning centuries and millennia. These prediction systems incorporated not just astronomical calculations, but historical analysis that correlated the appearance of paired objects with periods of technological advancement, social transformation, and cultural upheaval in human civilizations. Egyptian astronomical records preserved in temple inscriptions and papyrus manuscripts describe what they called the Boat of Ra and its hidden escort, paired celestial objects that appeared during dynastic transitions and periods of significant architectural and technological achievement. The Egyptian accounts emphasize the systematic nature of the Dark Companion's activities, describing it as conducting surveys that seem designed to assess human capabilities and social organization. The Egyptian texts are particularly notable for their detailed descriptions of how the hidden companion appeared to respond to human activities and technological developments. During periods when Egyptian civilization achieved significant advances in astronomy, engineering, or social organization, the Dark Companion was observed to alter its behavioral patterns in ways that suggested awareness of and interest in human progress. These correlations between paired celestial visits and human technological advancement appear repeatedly across ancient civilizations that had no contact with each other during the periods when these observations were recorded. The pattern suggests either remarkable coincidence or genuine relationships between interstellar visitation and the development of human technological capabilities. Norse mythological traditions preserve stories of Skirl and Hati, the cosmic wolves that pursue the sun and moon through the sky while remaining perpetually hidden from direct observation. While typically interpreted as metaphorical explanations for solar and lunar eclipses, these narratives contain specific details about the wolves' behavioral patterns that closely parallel the characteristics observed in Atlas's hidden companion. The Norse accounts describe Skirl and Hati as conducting systematic hunts that follow predictable patterns while remaining invisible to normal observation. The wolves are said to understand human attempts to track their movements and actively avoid detection, while continuing their relentless pursuit of their celestial prey. Most significantly, the Norse traditions describe periods when the wolves' activities intensify in response to human technological and social developments. The Edda texts contain mathematical relationships that describe the wolves' orbital characteristics with precision that seems inconsistent with the observational capabilities available to Norse astronomers. These calculations suggest that the Norse traditions may have preserved accurate observational data from earlier periods, when more sophisticated monitoring systems were available, or when the celestial phenomena were more readily observable. Celtic mythological traditions speak of the twin lights of the otherworld, paired celestial objects that appeared during periods of significant cultural transition and technological innovation. The Celtic accounts emphasize the complementary nature of these objects, describing one as a brilliant beacon that announced the approach of otherworldly visitors, while the other served as a hidden observer that studied human responses to the dramatic celestial display. The Celtic texts describe systematic attempts by druids and other astronomical observers to detect and track the hidden companion through indirect observation techniques that closely parallel modern methods for detecting dark objects near brilliant primaries. These ancient observation techniques suggest understanding of advanced astronomical principles that weren't supposed to be developed until the modern era. Chinese astronomical records spanning thousands of years of continuous observation contain extensive documentation of paired celestial visitors that appeared at regular intervals throughout Chinese history. The Chinese texts describe these objects as the dragon and its shadow, paired entities that conducted systematic surveys of human civilization while maintaining precise formation throughout their passage across the sky. The Chinese observations are particularly detailed in their descriptions of the Shadow Companion's systematic reconnaissance activities. The texts describe how the dark object would separate from its brilliant partner to conduct independent surveys of different regions, always returning to maintain precise formation relationships that suggested active coordination rather than passive orbital mechanics. Chinese records also document systematic institutional responses to paired celestial visitations, including efforts by imperial astronomers to conceal or minimize documentation of the Dark Companion's activities while maintaining detailed public records of the brilliant primary object. These historical patterns of selective information management closely parallel contemporary responses to the Atlas Companion discovery. The mathematical precision contained in Chinese astronomical records of paired visitors includes orbital calculations and trajectory predictions that demonstrate sophisticated understanding of interstellar mechanics. The Chinese observers understood these objects to be following hyperbolic paths that originated beyond their solar system, and calculated return intervals that operated across timescales spanning multiple dynasties. Mayan astronomical codices contain detailed mathematical models for tracking paired celestial objects that appeared during periods of significant cultural and technological development. The Mayan calculations incorporate complex cyclical patterns that correlate paired visitations with human technological advancement, social organization developments, and architectural achievements. The Mayan texts describe systematic efforts to predict the behavior of dark companions through mathematical analysis that combined astronomical observation with historical pattern recognition. These prediction systems achieved remarkable accuracy in anticipating when and where hidden companions would conduct reconnaissance activities, suggesting understanding of intelligence-driven behaviour rather than natural astronomical phenomena. Australian Aboriginal astronomical traditions, preserved through oral narratives spanning tens of thousands of years, describe paired celestial spirits that conduct systematic surveys of human activities while maintaining invisibility to normal observation. These traditions include detailed descriptions of the spirit's behavioural patterns, reconnaissance activities, and apparent responses to human technological and social developments. The Aboriginal narratives contain specific details about indirect detection techniques that allow careful observers to identify the presence of hidden companions through their effects on visible phenomena. These traditional observation methods closely parallel modern astronomical techniques for detecting dark objects near brilliant primaries, suggesting preservation of sophisticated observational knowledge across extraordinary spans of time. The consistency of these mythological traditions across unconnected civilizations, separated by vast distances and thousands of years, suggests shared experiences that transcend cultural interpretation. The specific behavioral characteristics described in these ancient accounts — systematic reconnaissance, formation-keeping precision, institutional concealment, and correlation with human technological development — match closely with the phenomena observed during Atlas's passage through our contemporary solar system. The mathematical precision contained in many of these ancient texts suggests access to observational capabilities or theoretical understanding that exceeded what should have been possible with the technology available to these civilizations. The possibility that these traditions preserve accurate records of actual astronomical encounters raises profound questions about the frequency and systematic nature of interstellar visitation throughout human history. The ancient emphasis on paired visitations, bright objects that draw attention while hidden companions conduct systematic reconnaissance, suggests that the Atlas encounter may represent not an unique event, but the latest iteration of a pattern that has been repeated throughout human history whenever our species has achieved sufficient technological development to warrant systematic study by intelligence from beyond our solar system. These mythological traditions also suggest that the institutional responses observed during the Atlas encounter — selective information management, systematic concealment of anomalous observations, and efforts to minimize public awareness of non-human intelligence represent continuation of institutional behaviors that have been practiced throughout human history whenever evidence of interstellar visitation has emerged. The ancient accounts paint a picture of a universe that is far more populated and strategically complex than modern science has acknowledged, filled with intelligence that conducts systematic study of developing technological civilizations through sophisticated reconnaissance missions that use brilliant displays to conceal intensive intelligence-gathering activities. In the convergence of ancient mythological traditions and contemporary astronomical observations, we glimpse the possibility that humanity has been subject to periodic systematic study throughout our developmental history, with each visitation timed to assess our progress and capabilities as we advance toward technological maturity that might eventually qualify us for more direct contact with the intelligence that has been watching us from the shadows cast by lights too brilliant to be anything but intentional misdirection. The shadow-following atlas may represent not first contact, but the continuation of a surveillance program that has been monitoring human development for millennia, using techniques refined through long experience with species that must be studied carefully before they can be trusted, with knowledge of their place in a cosmos far more populated and purposeful than they have ever imagined. In the gentle interplay between light and darkness that has characterized our encounter with 3i Atlas and its hidden companion, we discover fundamental truths about the nature of revelation and concealment that extend far beyond the technical details of astronomical observation or the theoretical possibilities of interstellar intelligence. The shadow that followed our brilliant visitor carries meanings that illuminate not just what we observed in the sky above our heads, but what we learned about the universe we inhabit and our place within its vast, purposeful, and perhaps eternally watchful expanse. Throughout human history, shadows have served as metaphors for hidden knowledge, concealed truth, and the presence of realities that exist just beyond the reach of direct perception. In the careful examination of Atlas's dark companion, we encounter these ancient metaphorical frameworks made manifest in the physical realm, a cosmic phenomenon that embodies the principle that what remains hidden often carries more significance than what blazes in obvious display. The philosophical implications of this shadow and light relationship extend to fundamental questions about how truth reveals itself in a universe where intelligence operates across scales and time spans that dwarf human comprehension. If Atlas served as a brilliant decoy designed to draw attention away from more sensitive reconnaissance activities, it suggests that authentic knowledge often hides behind spectacular display, requiring patience, subtlety, and indirect observation to detect and understand. This principle challenges contemporary approaches to scientific discovery that emphasize direct observation, immediate documentation, and public disclosure of all detected phenomena. The Atlas encounter suggests that the most significant cosmic truths may reveal themselves only to observers who understand the value of looking beyond obvious phenomena toward the shadows cast by extraordinary brightness. The universe may operate according to principles of strategic revelation that require more sophisticated interpretive frameworks than simple empirical observation can provide. The systematic concealment practiced by Atlas's companion also illuminates the relationship between knowledge and responsibility in a cosmos that may contain multiple technological civilizations at different stages of development. The shadow's careful avoidance of direct detection suggests awareness that certain types of knowledge can be disruptive or dangerous when revealed before observers are prepared to understand and integrate such information constructively. This perspective transforms the companion's stealth from simple deception into something more complex, a form of ethical intelligence gathering that seeks to understand human civilization without triggering defensive responses or social disruption that might interfere with natural developmental processes. The shadow may represent not hostile surveillance, but careful assessment conducted by intelligence mature enough to understand the responsibilities that accompany superior technological capabilities. The precision of the companion's formation keeping and reconnaissance activities reveals standards of patience and systematic thoroughness that challenge human assumptions about how intelligence operates across interstellar distances and extended timeframes. The Shadow's ability to maintain coordinated activities with Atlas across months of travel through complex gravitational environments suggests planning horizons and operational consistency that exceed anything in human experience. This temporal sophistication implies civilizations that think and operate across timescales that dwarf human institutional memory and planning capabilities. The Companion's mission may represent not a brief reconnaissance visit, but part of systematic observation programs that operate across centuries or millennia, gathering information about developing civilizations through patient accumulation of data that spans multiple generations of the species being studied. The ancient mythological traditions that describe similar paired visitations throughout human history suggest that our encounter with Atlas may represent continuation of surveillance programs that have monitored human development since the earliest periods of our technological advancement. The shadow following our contemporary interstellar visitor may be the latest iteration of systematic study that has been conducted with such subtlety that each generation of human observers has interpreted these encounters within their own cultural and technological frameworks without recognizing the underlying continuity of purpose. This possibility transforms our understanding of human history from the story of isolated civilization developing in cosmic solitude to something far more complex. The account of a species whose development has been observed, assessed, and perhaps guided by intelligence that understands the challenges and dangers that accompany technological advancement. The shadows that have followed bright celestial displays throughout recorded history may preserve evidence of cosmic mentorship that has operated through indirect influence rather than direct intervention. The institutional responses to the Atlas Companion, the systematic revision of observational data, the inadequacy of official explanations, the reluctance to acknowledge anomalous characteristics, reveal patterns of information management that suggest awareness among human authorities of implications that extend beyond simple astronomical curiosity. The careful concealment of evidence for non-human intelligence may reflect not conspiracy or deception, but recognition that certain types of knowledge require gradual disclosure to prevent social disruption. These institutional behaviours mirror the Companion's own strategic concealment, creating parallel systems of managed revelation that operate at different scales but serve similar purposes. Just as the shadow avoided direct detection while conducting systematic reconnaissance, human authorities may be managing the disclosure of cosmic intelligence in ways that protect social stability while allowing gradual acclimatization to realities that challenge fundamental assumptions about humanity's cosmic isolation. This convergence of concealment strategies, cosmic and terrestrial, suggests that the universe may operate according to principles of graduated revelation that recognize the psychological and social challenges that accompany paradigm-shifting discoveries. The shadows cast by brilliant cosmic displays may represent not just camouflage for reconnaissance activities, but systematic educational processes designed to prepare developing civilizations for eventual acknowledgement of their place in populated cosmos. The shadow's apparent success in conducting comprehensive reconnaissance while remaining largely undetected demonstrates the sophistication of intelligence that operates by principles we are only beginning to understand. The Companion's ability to map our technological capabilities, assess our social organization, and evaluate our readiness for contact was achieved through methods that left minimal traces in our detection systems, while gathering information that may be more comprehensive than our own understanding of human civilization. This asymmetry in knowledge and capability raises profound questions about the nature of cosmic relationships between civilizations at different levels of technological development. If the shadow successfully analyzed human society while remaining largely invisible to human analysis, it suggests that mature civilizations possess advantages in interspecies contact that may be insurmountable through technological development alone. The universe may contain hierarchies of intelligence that operate according to principles beyond simple technological sophistication. The Companion's systematic study of our solar system environment, its reconnaissance of gravitational fields, particle densities, and electromagnetic characteristics, suggests preparation for activities that extend beyond simple observation. The comprehensive mapping of our cosmic neighborhood may represent preliminary phases of more extensive engagement that requires detailed understanding of local environmental conditions and human technological capabilities. This possibility transforms the Atlas encounter from concluded cosmic visitation to preliminary phase of ongoing relationship that may unfold according to timescales and criteria that remain hidden from human understanding. The shadow's successful reconnaissance may have established foundations for future activities that will reveal themselves only when cosmic intelligence determines that appropriate conditions have been achieved. The most profound implication of the Shadow Companion may be its demonstration that the universe contains intelligence sophisticated enough to study us, without our knowledge, while patient enough to operate according to schedules that span multiple human generations. This suggests cosmos populated by minds that think and plan across time horizons that dwarf human historical experience, and operate according to ethical frameworks that prioritize careful assessment over immediate action. The meaning of the Shadow extends beyond the specific case of Atlas to encompass fundamental questions about how knowledge, power, and responsibility intersect in universe that may contain multiple forms of intelligence at different stages of development. The Companion's careful concealment may represent not just strategic camouflage, but ethical recognition that premature disclosure of advanced capabilities can be harmful to species that are not prepared to integrate such knowledge constructively. In the careful choreography of brilliance and concealment, revelation and patience, we encounter intelligence that demonstrates wisdom as well as technological sophistication. The shadow following Atlas may represent our first confirmed contact with cosmic intelligence, mature enough to understand that the most important truths often require careful preparation before they can be safely revealed. The philosophical legacy of this encounter may lie not in what we learned about interstellar technology or reconnaissance capabilities, but in what we discovered about the nature of wisdom, patience, and ethical responsibility in a universe where intelligence operates across scales that dwarf individual human comprehension. The shadow taught us that truth itself may operate according to principles of graduated revelation that respect the developmental needs of species that must grow into understanding, rather than being overwhelmed by knowledge they are not prepared to integrate. As we continue our own development as technological civilization, the memory of Atlas's shadow serves as a reminder that the universe may contain forms of intelligence wise enough to study us with patience and sophisticated enough to remain hidden until we demonstrate readiness for the responsibilities that accompany cosmic citizenship. The shadow that followed our brilliant visitor may represent not conclusion, but beginning. The first phase of relationship with intelligence that understands the value of waiting in darkness until we develop wisdom sufficient to appreciate the light. In the endless dance between revelation and concealment that characterizes our encounter with the cosmos, we learned that the most important messages may come not in blazing displays of obvious phenomenon, but in subtle influences that require patience, sophistication, and humility to detect and understand. The shadow following 3i Atlas reminds us that the universe may be far more populated, far more purposeful, and far more patient than we have ever imagined, filled with intelligence that chooses carefully when and how to reveal itself to species that must earn through wisdom and maturity the privilege of understanding their place in vast community of minds that spans the darkness between stars. Perhaps the greatest teaching of the shadow is that in a universe where intelligence operates across scales beyond human imagination, truth itself becomes collaborative endeavor that requires readiness from all participants. The light draws our attention, but the shadow carries the deeper message that we are not alone, we are being watched with care, and we are being prepared through patient observation for revelations that will come only when we demonstrate wisdom sufficient to receive them without being destroyed by their implications for everything we thought we knew about our place in the cosmic order.